Hello and welcome to lecture 12 of the course Theory of Computation. This is also the first lecture of week 3. Right. So, in the previous weeks we saw regular languages and we saw three characterizations for regular languages, like using DFAs, NFAs and regular expressions. So there are three models, and interestingly all these three models, even though they are different in their own ways, they turn out to have the same capability, meaning they all of them recognize the same class of languages, which are regular languages. So now the question is, how powerful are regular languages, right? How powerful are these models? Are there languages that cannot be captured using these models, right? So we know that all of them have the same power, but are there languages that cannot be captured by these models? Or is it the case that almost every language can be captured by this, right? So we want to understand what is the computational power of these, right? So pumping lemma is it gives us one way to understand, one way to answer this question, right? So pumping lemma is a necessary condition for languages to be regular, meaning if a language is regular, certain conditions have to be satisfied, right? It is necessary that certain conditions have to be satisfied. So in other words, if A is regular, right, then it says that A can be pumped. Okay, so I have put pumped in quotes because pumped is, when I say it can be pumped, it means it can satisfy the conditions, right? It is the necessary condition that I meant, right? However, this is only in the forward direction. It is not a necessary and sufficient condition. What I mean by that is the converse is not true. Just because A satisfies these conditions, or a language A satisfies these conditions, we cannot infer that the language is regular, right? So it's only necessary condition. So if A is regular, means A has to satisfy these conditions, or A has to be pumped. Just because A satisfies this condition doesn't necessarily imply that A is regular. However, what does the contrapositive give us, right? So this is the converse. The converse is not true. But what is the contrapositive? The contrapositive, right? So the above, or the contrapositive of the above, right? So the above in contrapositive. So what is the contrapositive? The contrapositive is that if A cannot be pumped, then A must necessarily be not regular, right? So P implies Q, the contrapositive is not P implies not Q. So the contrapositive here is if A cannot be pumped, then A is not regular, right? So this means that if A cannot be pumped, A is not regular, right? So maybe I will highlight that. Right. So now this is a way to show that certain languages are not regular, right? So now if we show that a language cannot be pumped, then it implies that the languages are not regular. Once again, it is only the contrapositive that is true. For any statement, the contrapositive is true. The converse is not true, right? So just because A can be pumped, we cannot infer that a language is regular, right? So it's only a necessary condition, which means that if it does not meet this condition, then we can infer that the language is not regular. The converse is not true, right? So just because it satisfies this condition, we cannot infer that the language is regular. So let's before we get on to the formal statement of the lemma, pumping lemma, right? Let's just see an example of a language that is not regular, right? So the language is the language B, where B is 0 power n, 1 power n for any n greater than or equal to 0, right? So this is the language. So when n is 0, it is just the empty string. When n is 1, it is the string 0 1. When n is 2, it is 0 0 1 1. Then 0 0 0 1 1 1 when n is 3, and so on. So there are infinite strings here, right? For each value of n, there is a string here. We have n number of zeros followed by n number of ones, right? So it's a very clearly defined language. So it's very easy to understand what this language is. Interestingly, this language is not regular. It's a simple enough language, but interestingly, it's not regular, right? So the reason is that So a DFA, so if it is regular, then we know there is a DFA that recognizes this language, right? So now the DFA has to, in some very vague sense, it has to check how many zeros are there, followed by how many ones are there, right? So, and it has to be equal. So first of all, the string has to be of the form some zeros followed by some ones, right? And then it also has to be it also has to be checked that the number of zeros and the number of ones are the same, right? So which means and we know a DFA can only scan the string once. So it means that we have to count the number of zeros, and then we'll start the number of ones, and then we have to kind of check that they are the same. But what can n be? So this is an infinite language. N could be arbitrarily large. N could be like n could be 1000, n could be million, right? So if you give me a DFA with, let's say, 100 states, it cannot keep track of a huge count, of a count of million with 100 states, right? So if you give me a DFA with a fixed number of states, I'll give you a string where n is really large, that it will be kind of clear that this relatively small size DFA cannot keep track of such a big count. So that is the reason. That is the reason why we cannot that's kind of an intuition why this language is not regular, right? So there is still not a formal proof, right? Perhaps it doesn't need to count; it can do some other thing. Perhaps somehow it without counting itself, it's able to do something using some strange modular arithmetic or something like that, right? So how do we know that we indeed have to count? So that's another valid question. But but then this is just an intuition, right? So let's see. Pumping lemma will tell us that will give us a clear proof that this is not regular, right? So we'll not see the proof in this lecture. We'll see the proof in the next lecture. But in this lecture, we'll see the pumping lemma itself, right? Right. So this is still an intuition, right? So this one has to remember, right? This is still an intuition. So we cannot say that it has to count. And pumping lemma gives us a way to formalize this, and this is pumping lemma for regular languages. We'll also see another version of pumping lemma for context-free languages a few weeks from now, right? It's not the same, but it's something similar. What we are seeing now is pumping lemma for regular languages. It gives us a necessary condition for regular languages. It was discovered by Michael Rabin and Dana Scott in 59, followed by Bar Hillel, Perles and Shamir in 61. In those days, it was like the science used to travel slow, like we didn't have electronic communication. So it was very common that somebody discovers this and somebody else also discovers the same thing, right? So independently, right, because things have to be studied, published, printed, and then journals, books have to travel across the globe and so on, right? Okay, so now let's get to what the pumping lemma is, right? So pumping lemma, this is a statement in the book. It's theorem 1.70. If A is a regular language, then there is a number P which is called the pumping length, such that for any string S in A that has length at least P. So by at least I mean greater than or equal to P. Then we can split S into three pieces, X, Y, Z, or S can be written in this manner, X, Y, Z, such that the following three conditions are satisfied. What are the three conditions? Consider the string X, Y power I, Z. Okay. For each I, consider the string, and all of these strings are in A. So maybe I'll just so when I is 0, this gives us the string XZ, right? So XZ is what we get when I is 0. When I is 1, it gives us XYZ. When I is 2, it gives us XYYZ. When I is 3, it gives us XYYYZ, and so on, right? So this is an infinite family of strings. What it's saying is that all the members of this family must be in A, right? So what it's saying is that if A is a regular language, there is a pumping length such that you give me a string of the pumping of length at least as much as the pumping length, then there should be a way to divide it in such a way that divided to x, y, z such that now you repeat y twice. So in x, y, z y comes once. You repeat it twice, thrice, 4 times, even 0 times. All these strings x, y, x, z, x, y, z, x, y, y, z, all of these strings are in A. So we know that x, y, z is in A because x, y, z is equal to s, and by the statement itself we chose s to be a string in A, right? But what it is saying is that all the other strings, in fact an infinite number of strings, all of them have to be in A, right? And further, 2 more conditions. Y, the length of y is strictly greater than 0. In other words, what it is saying is that there is only one string of length 0, which is the empty string. So in other words, it's saying that y is not the empty string, right? So it cannot be the empty string, it could be any other string that has at least length 1. And the third condition says that length of x and y put together has to be at most p, less than or equal to p. Okay. So once again, if A is a regular language, there is a pumping length such that any string that you take in the language of length at least p, there is some way to divide the string into 3 pieces x, y, z such that these 3 conditions are satisfied. So condition 2 and 3 are length conditions on the length of y and x, right? It says 3 says that x, y has to be at most p, 2 says that y has to be non-empty, and the condition 1 says that there has to be the x, y power I, z is in A, meaning x, z is in A, x, y, z is in A, x, y, y, z is in A, x, y, 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 z is in A, and so on, right? So any string that is of length at least the pumping length can be split in a manner that satisfies these 3 conditions. That is the pumping lemma. Now the way to show that a certain language is not regular is that we will have to for that language we will have to come up with a string which we cannot split in a way that meets these conditions, right? So informally we say that string cannot be pumped, right? So let's see why this is true. Why is it the case that there is some length beyond which any string can be split in this manner, right? So that's the proof. Let us see the proof, right? So what I will be describing here is kind of an informal proof, or I won't say sketch, but somewhat developed sketch of the proof, right? Because I think that is much easier to communicate. There is a formal proof in the Sipser book, right? So in the Sipser book, but the formal proof is more notations and formalisms, but what I am going to explain is somewhat more informal, but it's pretty much the entire proof, right? But it's I think for instructive purposes this is better, right? So we have a regular language A, and then we have to show that there is a pumping length such that the following conditions are satisfied. Because the language is regular, we can assume that there is a DFA M. Let Q be the set of states and sigma delta Q1 F, right? So Q1 is the starting state. Now, what the pumping length will be the number of states. Okay, so I'm upfront telling you the pumping length. So we know that DFA means it's a finite set of states. So Q is finite, capital Q. So pumping length P is the size of Q, cardinality of Q, in other words the number of states. So let me ask you a simple question which is like a basic question on logic or something. What if all the strings are of length at most P? Meaning all the strings are of length. So pumping lemma talks about strings greater than or equal to P, right? Of length greater than or equal to P. So what if all the strings are of length strictly less than P, right? So if all the strings are of length less than or equal, strictly less than P, then let's read the statement. If A is a regular language, then there is a number P such that if any string is of length greater than P, then this has to be satisfied. So if let's say we take an S that does not meet this condition, that is of length less than p, then nothing has to be satisfied. So this is a situation where we say the statement is vacuously true, right? So if p then q, right? So let's say there's a statement of the form if a then b. Okay. Now suppose nothing, the condition a itself is not satisfied, then trivially the statement is true, right? Because a itself is not satisfied. So it's like saying if it rains today, I will give you 1,000 rupees. Suppose it doesn't rain today, then the statement is true even if I don't give you 1,000 rupees, right? Because it was a conditional statement. The condition itself was not met. Similarly, if all the strings in the language are of length less than p, strictly less than p, then the statement is true in a vacuous sense or in an empty sense, because the condition itself is not met, right? So then pumping lemma holds vacuously, right? So vacuously right, so meaning in an empty sense, right? Because the if condition itself is not satisfied. So suppose there are strings of length at least p, right? Suppose a contains strings of length at least p greater than or equal to p. Then let's see how to deal with it. So let's consider some string s, right? So let's say s has length n, and here I have written s as s1, s2 up to sn. I am writing each symbol, right? So where like symbol by symbol. So length of s is equal to n. So this is each symbol, and symbol by symbol I am writing. S1 is the first symbol, S2 is the second symbol, and so on. Now let's see the machine how it processes this, right? So before reading any symbol, the machine, let's say it's in state q1. It has to be in state q1 because q1 is the starting state of the machine, right? So before reading any part of the symbol string s, let's say the machine is in q1. After reading s, let's say it transitions to q3, and then it goes to q9, right? After reading s1, s2, then let's say q16, q12, and so on. And finally, after reading all the n symbols, it ends at q13. Okay, so this is just some numbers that I am taking. Okay, so the actual q1. So the first state has to be q1 because it's starting state, and let's say it ends at some state, let's say q13. What do we know about q13? One point is that it is a string that we assume to be in the language. So which means the DFA will accept the string because it is in the language, and the DFA is for that language. So this has to be an accepting state, right? So this has to be an accept state of n. Because the string is in the language. So we know q1 is a starting state, we know q13 is one of the accept states, right? Now let's see how many such states are there, right? So how many states are there? So there are n symbols here, and you start with something, and after each symbol is processed, there is one transition, you get one more state, and there are n plus 1 such states listed here. And out of these n plus 1, I am not claiming that all the states are distinct, right? So there could be, so I am just saying that there are n plus 1 states appear, right? Some of them could be repetition. So I'll highlight that with some possible repetitions. Now the point is, if the length of s, which is equal to n, is at least the pumping length, at least p, right? Suppose n is at least p, which I mean by that, I mean that n is greater than or equal to p. Then there are at least p plus 1 states listed here, but you remember we chose pumping length as the number of states. So if we write p plus 1 states, we know that the machine itself has a equal to p states. So if you write p plus 1, or more states, we know that the machine itself has p states, so something has to repeat, right? Without, like, let's say you write a 11 digit number, at least some digit has to repeat, because we only know 10 digits, 0, 1, 2, 3 up to 9, right? So like that, there has to be at least one repeated state, right? Because the S is long enough. And in the manner I wrote this particular string, the repetition happens with Q9. Okay, repetition happens with Q9. It is seen after S2 and it is seen again after S5, right? So now let us do the following. Now let me call, I'll call the string from till the first occurrence of Q9 as X. From the first occurrence till the second occurrence, I'll call it Y. And from the second occurrence to the end of the string, right? So till the end of the string, I call it Z. So here in this figure, X is S1, S2, right? S1, S2, Y is S3, S4, S5, and Z is S6, S7 up to Sn, right? So the rest of the string. So X again is the string till the first time Q9 occurs, Y is the string from the first till the second occurrence of Q9, and Z is the rest of the string, right? So now let's see what X, Y and Z are doing, right? So upon reading X, the machine transitioned from Q1 to Q9, right? So it went from Q1 to something, then to Q9. Upon reading Y, it started from Q9, right? So before reading Y, it was at Q9, then it went to Q16, Q12, finally it came back to Q9, right? So X moved the machine from the start state to Q9, Y started from Q9 and took it through some states and brought it back to Q9, right? And Z took the machine from Q9 to Q13, which is an accept state, right? So let's try to maybe draw it, depict it pictorially. So let's say X does this, Q3, Q9, right? And then let's say some states, Q9 does something, right? And right, so X takes it from X takes it from Q1 to Q9, Y takes it through the circle, right? So through some states and then comes back to Q9, and Z takes it from Q9 to Q13. So notice that Q13 is an accept state, so I have drawn the double circle, right? So this is what happens, this is what each of these substrings does, and together X followed by Y followed by Z is equal to the string, right? So S is equal to X, Y, Z. So what did we do? We first of all claimed that if the string is of length, at least the pumping length, some symbol has to appear, repeatedly, meaning 2 times at least. Now you look at the first occurrence of that symbol and the second occurrence of that symbol, right? And then you consider start of the string to the first occurrence as X, first occurrence to second occurrence as Y, and second occurrence to the end of the string as Z. Now the claim is that this split X, Y, Z satisfies the conditions of the pumping lemma, right? So all we used was that there is a DFA for the language, and then we set the pumping lemma to be this number of states, and that in turn gave us everything, right? So this is again same thing that I said earlier. X takes M from Q1 to Q9, Y takes M from Q9 to itself, and Z takes M from Q9 to Q13, which is an accept state. So maybe we'll put double circle here as well. Now let's see what if instead of x, y, z, what would have happened if I had x, y, y, z? So x would have taken from q1 to q9, y would have taken from q9 to itself. Again, y would have taken one more round through the same path. So two y's, and then z would take it to accepting state. Again, if I had x, y, 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 z, again same story. Instead of 2 rounds of y, we would have 3 rounds of y. Even if x, z, x would take from q1 to q9 and z would take from q9 to q13. So all these strings x, x, z, x, y, y, z, x, y, 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 z, all of these would be accepted by the DFA, right? So which means that all of them are in the language, right? So which means x, y, all of these strings that I wrote, x, z, x, y, y, z, x, y, 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 z, all of them are in the language, because the DFA is a DFA that DFA for the language. So anything that is accepted by the DFA is in A. Hence we get that all the strings x, y power I, z, right? So whatever I wrote are the strings in x, y, y power I, z, they are all in the language. Right? So this is the condition 1 of pumping lemma. Now we have to show that y is non-empty and xy, length of xy is at most p, which is not that hard. And we know that there are 2 occurrences of the of some state. So between the 2 occurrences, let's say q9, the closest that these 2 occurrences can come is just before a symbol and after a symbol, right? And this length, the string y is from the first occurrence to the second occurrence. So the first and second occurrence are at least 1 symbol apart, right? Because at least 1 symbol is needed. Hence there exists at least 1 symbol for y. So y, the length of y cannot be 0. It has to be at least strictly greater than 0. In other words, it cannot be the empty string, right? And finally, we want to show that the length of xy is at most p, right? So to ensure that, what we do is we look at the first p plus 1 we look at the first p plus 1 states here, right? We look at the first p plus 1 states. In other words, we look at the first p symbols of the string. The first p symbols of the string itself takes it to p plus 1 states, starting from the starting state, second state, third state, after reading the pth symbol, it will be in the p plus 1 state. So already there are p plus 1 states, but in the p plus 1 states that the DFA traversed, but we know that the DFA has only p states. So we know for sure that even after reading the first p symbols, there some state has to repeat, right? So which means that, so what I am saying is, this means that by pigeonhole principle, there must be some repetition occurring before the pth symbol of the string, right? So pigeonhole principle is something saying that, like, if there are 10 objects and 9 holes, you put the objects into holes, there are at least 1 hole has to have 2, right? So here we have p plus 1 states, but we know that actual number of states are only p, so some state has to come twice, right? So before we reach the pth symbol, or at the time we reach pth symbol, there has to be a repetition. So we know that, so what is x and what is y? Y is the x is the part from the beginning to the first time the symbol repeats, the state repeats, and y is it from the first time to the second time. So xy is at most p symbols, right? So which is what the third condition is, xy, length of xy is at most p, and that is all. So because that is the third condition, and that first part is xy power I z is an A, second is y is non-empty, and third is the length of xy is at most p. These 3 conditions together form the pumping lemma. So this is fairly, I think fairly rigorous, though I present it in a somewhat informal way. You may have a look at the formal proof in the book, which is quite notation heavy but very terse, like just 2 short paragraphs, but it conveys the same message. So just to understand the formalism involved, I suggest that you go through the proof, and once you have the informal idea, it should be much easier to understand what is going on if you read the terse proof, if you read the proof in the book after listening to this presentation, right? So just to summarize, pumping lemma for regular languages is a necessary condition for the languages to be regular. It is not a sufficient condition. So if a certain language does not meet the conditions of pumping lemma, or it cannot be pumped, then we can infer that the language is not regular. It is not a sufficient condition. Because it meets the conditions, we cannot infer that the language is regular. It's only necessary condition. We can only use this to show that languages are not regular. We cannot use this to show that languages are regular, right? So it says that if A is a regular language, then there is a pumping length, and any string that is of length greater than the pumping length can be split into three pieces x, y, z, such that these three conditions are satisfied. And the main idea of the proof was that so first of all, if the language is regular, then there has to be DFA. So that suppose the DFA has 10 states. Now you consider a string of length at least 10. We know that when processing the first 10 symbols, the DFA traverses through at least 11 states. So some state has to repeat, and using this repetition, which has to occur in the when first 10 symbols are processed, using this repetition, we figure out the splits x, y, and z, and that it's quite easy to see that it meets these conditions. So that's the summary of the proof and of the pumping lemma. So in the next lecture, we will see some illustrations, some examples of how pumping lemma can be used. Thank you.